Okay, good evening, everybody. My name is Chandru Merchandani, the Programs Director for the Incose Chesapeake chapter. Today, we are going to have a pretty interesting talk. A human-induced climate change is not a theory, it is a reality. The role of the engineers is essential to help saving the world through transition to low carbon. Our speaker is Bob Watson, and he's going to present an unambiguous evidence that humans are changing the Earth's climate. I'll let him talk a lot more about that. So let me tell you something about him. He's a semi-retired environmental scientist. He's worked as a senior scientific advisor at NASA, as head of the mission to Planet Earth, at the White House as Associate Director of Environment in the OSTP, World Bank Chief Scientist, and the UK Government Chief Scientific Advisor for DEFRA, and chaired assessments and co-chaired a series of national and international scientific and technical assessments, stratospheric ozone climate change, intergovernmental panel on climate change, biodiversity, and agriculture, intergovernmental assessment of agriculture, science, and technology for development. So you'll notice not only is he talking as a scientist, but he's also talking from the point of view of the stakeholders. So without much ado, I'll ask Robert to come and talk.
I'd like to talk about climate change today. And so there's absolutely no doubt whatsoever the evidence is strong that we are changing the Earth's climate. Temperatures are getting warmer, seeing changes in precipitation patterns, extreme weather events, and sea level rise. There's also no doubt that nearly all of these effects across the globe are harmful. There are some places where agriculture gets better with slightly warmer temperatures, longer growing seasons. But in general, the major impacts of climate change are harmful, and they actually affect quite seriously these Sustainable Development Goals, which I'll talk about later. There's a Paris Agreement that every country in the world, except about one, signed about 18 months ago, although Trump has actually pledged to take the US out of the Paris Agreement, and I'll talk about the Paris Agreement. I'll talk about the Paris Agreement and what it is. And clearly, the time for action is now. All countries, not just large developed countries, but all countries need to transition to a low-carbon economy if we're going to avoid human-induced climate change getting any worse than what it already is. We also need effectively to adapt. How do you get more resilient agriculture? How do you get more resilient water resources? So, first part of it, why have we got climate change? These are the emissions of carbon dioxide that come from the burning of coal, oil, and gas. There are other emissions which I'll mention in a minute. But clearly what you can see is since 1990 and before, a very significant increase in the emissions of carbon dioxide at a global level. We thought it was starting to peak, but 2017 was another 2% higher. So the gases are clearly increasing due to our energy use. This shows you which countries are predominantly responsible for it. Until about when we started really being serious about climate change in the 1960s, 1970s, it was predominantly the US and Europe. Since then, a monstrous increase because of the build-up of the energy system in the industrial sector in China. China now is the single biggest emitter of greenhouse gases, especially carbon dioxide, in the world. The US, if anything, has gone down slightly, so has Europe. India is growing, but clearly not to the level at the moment of China. If, however, you do say, what are the emissions per capita? The US still is the largest single emitter in the world per capita. Luxembourg is very similar, so is Australia. But China, while increasing rapidly, as you can see, because individual wealth is increasing, as well as just the economy as a whole. But per capita, the US still uses more greenhouse gas emissions, or emits them, than any other country in the world. And the third way to think about it is effectively how efficient is industry. So what are the carbon dioxide emissions per unit of economic growth? And as you can see, China, back in the 1970s, very, very inefficient. very low productivity per unit of energy used, which is nearly all fossil fuel. But boy, it's really increased its efficiency very significantly. Still worse than the US and Europe and India, but clearly improving its efficiency quite significantly. They are starting to decouple economic growth from energy and economic growth from emissions of carbon dioxide, which is clearly what is needed. 91%, and this is a period of a decade, 91% of the carbon dioxide came from burning of fossil fuels, and about 9% from deforestation, cutting down the world's forests, mainly in the tropics. 44% of the emissions stay in the atmosphere, and I'll show that in a second. 31% actually gets absorbed by the terrestrial biosphere, predominantly the above-ground biomass, trees, vegetation, but some eventually by soils. And about a quarter is actually absorbed into the ocean. And this last part is actually critical. It helps to mediate climate change, but it also has some very adverse effects that I'll mention in a couple of minutes. So this simply shows you, as you have the emissions of carbon dioxide go up, the atmospheric concentration just goes up and up and up, and it's still going up. The reason you see this up and down is effectively, this is Mauna Loa in Hawaii, and so you get a seasonal cycle of the uptake of carbon dioxide by vegetation in the summer and the release in the winter. So there's an annual cycle around what is most important is the long-term trend. This slide basically shows temperature. The black line, so land surface, the black is the observed temperature on the land surface across the globe. This is the average, or the sum of land and ocean. And this shows you different regions in the world. But what you notice in every one of these slides, the black is going up. Temperature has increased just over 1 degree, in the last 100 years. Then you see a blue line, or a blue swath, and an orange. The blue is where we try to simulate the observed change in temperature on natural phenomena alone. Changes in solar output, changes in volcanic activity, and as you can see, there is no correspondence between the black line and the blue simulation. We then have a climate model that simulates not only natural phenomena, as I said, solar variability and volcanic activity, but also putting greenhouse gases into the Earth's atmosphere, carbon dioxide, methane, nitrous oxide, fluorocarbons, changes in land albedo, also quite critical. When you put all of those in, you get the pink line. And as you can see, at a global level for land, global level for land and ocean, or even at the regional level, there's a pretty good correspondence between the observed temperature and the simulated, as long as you invoke human activity. The other way to say it is the blue line. You cannot explain the observed changes in temperature on natural phenomena alone. We've also now seen effects all around the globe of human-induced climate change. We've seen changes in the physical system. Glaciers are retreating, snowpacks are retreating, the river flows changing, floods are changing, and you're seeing major coastal erosion in low-lying areas of deltaic areas throughout the world, Bangladesh, China, Egypt, as well as sort of small islands. We're seeing biological systems affected. Our terrestrial ecosystems and marine ecosystems are being changed, and human-managed systems such as food production clearly are being affected already by human-induced climate change. So what could happen in the future? This is what we call, and don't worry about what RCP means, this is a low emission scenario, trying to really move away from using fossil fuels, using more renewable energy, also using energy much more efficiently. So a low emission scenario. This is what I'd call business as usual. We carry on producing our energy using fossil fuels, not using very much renewable energy, and also not improving end-use efficiency very much. So what you see in a low emission scenario, you do see increases in temperature, between the base period, 1986-2000, to the end of the century, 2081-2100, but relatively low, typically 1, 2, up to 3 degrees Celsius. Also see changes in precipitation patterns, but again, relatively modest, plus or minus 10, 20, 30%. And that's the world we have to aspire to. We can't eliminate or stop human-induced climate change, but we can, if we go to a low-emission scenario, try and limit future change. This is the high emissions, or what I call business as usual. What you can see here, land mass, and there's two, it's the same there, but it's more pronounced here. Land masses were more than the ocean, the dark red more than the oceans, and the high latitudes were more than the equatorial region. And here, as you can see, very large projected changes in temperature, 4, 5, 6 degrees Celsius on land masses in the USA, right across Asia, Africa, parts of Latin America, Australia. Also, some significant changes in precipitation where the high latitudes get wetter and the dry areas of the semi-arid areas in the subtropics get drier. So it's a perverse situation. The wet areas of the world become wetter and the dry areas become drier. Sea level, again, for these various scenarios, low emissions, potentially up to 0.5 meter sea level rise. The high emissions potentially at least, potentially closer to 0.75 meter. The basic problem with sea level rise is once you kick it in motion, it will actually go up for hundreds, if not thousands of years, and you can't actually turn it around. So the sea level rise has a huge inertia in the exchange of energy between the atmosphere and the ocean. There's actually 3 reasons you get sea level rise, the 2 dominant ones which I should mention. One is just thermal expansion of the ocean. You heat water and it expands. And the other one is all the land glaciers tend to start to, including Greenland, West Antarctic ice sheet, start to melt. So there's a couple of reasons you start to see these projections of sea level rise. As I mentioned, the oceans absorb some of the carbon dioxide that comes from the burning of fossil fuel. It goes into the ocean, it forms carbonic acid. The oceans become more acidic, major adverse effects on coral reefs and all shellfish. So the fact that the oceans absorb some of the carbon dioxide is good to limit the amount that stays in the atmosphere, but it comes at a cost of acidification of the oceans. So what are the real challenges we face? What are the projected impacts? Well, higher temperatures, more variable precipitation will give more floods and droughts. And what happens on precipitation is there will be more heavy precipitation events, leading to potentially more droughts, and there'll be less light precipitation events, which actually leads to droughts. So in the same geographic location, anywhere in the US, in a single year, you may have floods and droughts. What does that do? Largely affects agriculture and largely affects water resources, both quantity and quality of water. Human health adversely affected, vector-borne diseases such as malaria and dengue, not an issue in the US, but a major issue in the tropics and subtropics. Waterborne diseases such as cholera, heat stress mortality, which a major event was in Chicago just over a decade ago. Hundreds of people died in a 3-day spell because temperatures became over 90 degrees day and night. And poor people, socioeconomically disadvantaged without air conditioning, just couldn't cool off at night. Europe had a huge event a couple of years ago of heat stress mortality. And then also, one doesn't think about it, malnutrition. Because you have reduced food in many of the developing countries due to the higher temperatures and also droughts, more people will suffer from malnutrition in developing countries. Not an issue in the US, but a major potential issue in many developing countries. And then, of course, you get extreme weather events with high winds, flooding, etc., hurricanes, which we've seen, of course, Hurricane Sandy that hit New York, Katrina that hit New Orleans. Soil erosion, a major issue. Landslides, often see them in California. Sea level rise will affect coastal infrastructure and also saltwater intrusion affecting water quality and again agriculture. Ocean acidification I've already mentioned, affecting fisheries and coral reefs. And the warmer temperatures, major impact on biodiversities at the genetic species and ecosystem level. Cost of climate change, I'm not sure how good these numbers are. One has to question them. But potentially, by the end of the century, due to sort of a serious hurricane damages, real estate loss, etc., could be a couple of % of GDP. And so there are these so-called 17 United Nations Sustainable Development Goals. I'm only showing about 10 of them. Climate change, and the other issue I work on, which is loss of biodiversity, has a major effect. Climate change really affects poor people in developing countries. It takes away some of their livelihoods. It basically means we're not going to end poverty in many developing countries. It also undermines food security because there'll be less agricultural productivity in developing countries. I've already talked about healthy lives, vector-borne, water-borne diseases, heat stress. Water quantity and quality will be adversely affected, especially in many developing countries. Infrastructure, including in parts of the US, will be badly affected, especially if you go to up to Alaska. The permafrost is basically breaking apart, same in Russia, therefore it affects infrastructure such as roads. Also, when you think about sea level rise, a major threat to port infrastructure, seawall defences. Major issue of inequality within countries and amongst countries. Poor people always suffer most with these type of environmental issues, even in the US. But when you look across the world, it's poor people in poor countries that effectively are most affected. Human settlements, as I've already mentioned, if you're near a coastline, a low-lying coastline, such as deltaic areas, a major effect of sea level rise. And biodiversity, these two here, really badly affected by changes in temperature, changes in ocean acidification, changes in precipitation. So basically, climate change, we are changing the Earth's climate due to human activities. It will continue to change. The only question is how much can we limit that future change? And therefore the question is, can we and how can we transition to a low carbon economy, get out of using fossil fuel? The impacts of climate change are, as I've already said, primarily negative and will only get worse in the future. So we have to adapt. As I said earlier, how do we have resilient agriculture? How do we have resilient water systems? Resilient infrastructure? I'm not going to go into that anymore. I'll focus on mitigation. I've already said this about poor people being most vulnerable. And this is the key point. Climate change is an environmental issue, but it's also an economic, social, development, moral, and ethical issue. It really is a significant threat to the future human well-being. So what's the challenge of meeting the so-called Paris 2-degree target, which I'll talk about? These are the major documents that really have done a very good way of analysing. This is the IPCC document that looks at mitigation, basically, as well as adaptation. There was a global energy assessment put out a few years ago, and this is a document I put together on behalf of small island states and was presented to the heads of state in a meeting in New York about two and a half years ago. So the point basically is the scale of the challenge of totally changing the world's energy system is quite significant, but it is totally doable. But it is something more than we've ever tried to do. It's the rate of changing the infrastructure that's the real big challenge. It's not how to change it, it's the rate we need to change it without basically forsaking a good capital stock. So we need to be bold if we're going to meet the political goal of 1.5 to 2 degrees Celsius. That is to say, the goal is how do we limit human-induced climate change averaged across the globe to no more than 1.5 to 2 degrees Celsius relative to pre-industrial 1850. We're already 1 degree warmer already. So it's only a question of can we limit future change to only 0.5 to 1 degree. The question is, how do we do it without significantly increasing the cost of mitigation and adaptation, and how do we avoid technological lock-in? Therefore, we must transition away from fossil fuels as soon as possible. How do we actually, for poor people in developing countries who need access to modern energy, how do we provide them access without relying just on fossil fuels? We have to recognize there is technological, institutional, financial, and political inertia in all countries of the world, both developed and developing. And fundamentally, time is running out. It's a very straightforward challenge. So, fairly often, there are significant cost-effective to increase energy efficiency. Increase energy efficiency in the transportation sector, the building sector, and the industrial sector. It's really clear we can move to electric cars if we wanted to by 2030. The big challenge is putting the infrastructure in place for an all-electric car fleet. But we can do it. We can improve the efficiency of our housing stock very, very much. The problem there on the housing stock is retrofitting existing buildings. Putting a new building up, you can make it phenomenally efficient. It's how do you actually retrofit old buildings. But fundamentally, end-use efficiency is a major part of the solution to human-induced climate change. Deployment of renewable energy, especially wind and solar. Also, hydropower, both mini hydropower and large-scale hydro, can be both good for climate and environmentally sound. Large hydro can, if it's not done well, be really bad for the environment, bad for people being displaced by large-scale hydro. But basically, renewable energy has to be one of the ways of the future. We literally do need to put a price on carbon, and that is if you're going to burn coal, oil and gas, it has very adverse social, environmental and economic impacts. We should internalize that price into the price of carbon that would then stimulate the markets for renewable energy. We need system-wide transformation, and that requires a significant change in policies, and we also need to catalyse behaviour change. Individuals, community, private sector, and governments themselves. And therefore, the large conclusion is no more coal-fired power plants should be without carbon capture and storage. And what I mean by that is you can combust oil, gas, coal, produce electricity, but then you need to capture that carbon dioxide before it's emitted to the atmosphere and you then liquefy the carbon dioxide and you subduct it in a depleted oil well, gas well, or effectively in a saline aquifer. So you can, in theory, still continue to use fossil fuels as long as you join it with carbon capture and storage. But so we need some more research done on this, both what is the efficacy, what's the energy penalty, what's the financial penalty, to what degree will a saline aquifer or a depleted gas well hold the carbon dioxide and not release it to the atmosphere. So there's still some research needed to be done on this particular issue, but it does look potentially promising. I'm going to flick through these. So these are the sort of various emission scenarios out to 2100 that we do. They're different sort of assumptions based on demographic change, population, economic change, how fast will the world's economy grow, to what degree will we still rely on fossil fuels, and to those scenarios where we almost eliminate fossil fuels. So they are the various scenarios that the world is looking at, and they're all plausible. If anything, we're currently on this upper line. We're not on one of these lines going down. So what did the Paris Agreement say? Which, as I say, every country in the world basically signed, although Trump has threatened to pull out of it. It says we should limit greenhouse gas emissions such that we limit temperature increase to 2 degrees Celsius and even try to limit to 1.5. My personal view is we don't have a hope in hell of 1.5, and I don't think we've got a hope in hell of 2 degrees Celsius. Technologically, they're both feasible. I don't see the politics in place to achieve either. We should peak our emissions as soon as possible. In other words, they need to peak now globally. That's not going to happen. We need to adapt. I'm glad everyone recognizes there's a need for adaptation as well as mitigation, and a real sticking point. developing countries do need to be funded by developed countries, the financial resources. And what has been promised is the developed world, US and Europe, will provide $100 billion a year to developing countries for mitigation and adaptation. I don't see where that money is going to come from. I really don't. I'm really worried this is just, we'll promise to pay, and that money will never, ever materialize. So this is what I call business as usual. Here we are. This is greenhouse gas emissions, gigatons of carbon dioxide equivalent. We managed to bring in methane and nitrous oxide into this thing called equivalency. Here we are in 2010, 47.5 gigatons of CO2 equivalent per year. Business as usual, if we don't do anything, we'll be up here. To hit a 2-degree target, we need to be coming down here by 2050. And for 1.5, we actually need to be somewhere down here. So where are we? I've just expanded it. Okay, so governments have got some current policies that does suggest we're moving away from the so-called baseline. That's good. In Paris, there was a whole bunch of countries that said, we'll do even more, but it only brings us to there. Then some other countries said, we'll do even more, but it's conditional on the $100 billion and technology transfer. Brings us to here. But that's what's been promised. Now, I actually don't believe that we're going to meet either of those. I don't think everyone will step up to the plate, including the US, given Trump doesn't believe, and many Republicans in the Senate don't believe climate change is a serious issue. So I actually don't believe we'll meet these targets here. But the basic point is, even if we did meet those targets, we're way above what we need to be for the 2 degrees Celsius by 2030, and the 1.5, as I say, would need to be down here. So we've got a major emissions gap, a major emissions gap. So my conclusion in a paper I wrote a few months ago was, what is the truth? Well, it's a very, very important step, and I applaud governments for recognizing how serious it is. 189 countries pledged to try and achieve the 2-degree target, but as you just saw, their pledges are inadequate, and therefore they literally need to double or triple the scale of effort to reduce greenhouse gas emissions. The calculation I did, and has recently been endorsed by many other people, will hit 2 degrees, I would say actually by 2060. So the 2050 is probably wrong. I'd say about 2060, 2065. And the 1.5 goal, we're going to pass it in the early 2030s. There is zero chance, in my opinion, of hitting the 1.5 goal, basically. If we don't do anything additional to what was pledged in Paris, we're going to go to 3 to 4 degrees Celsius, way above the goal of 2 or 1.5. So this just shows you another view of the greenhouse gas. This is carbon dioxide from fossil fuels. You've seen it before going up. This is our carbon dioxide from land use change, primarily deforestation. This is methane that comes from emissions from leakage of natural gas lines, also methane from rice paddies and enteric fermentation, primarily in cattle, but also a little bit in sheep. Nitrous oxide primarily comes from agricultural use of fertilizers. So we not only have to get to grips with carbon dioxide, but also with the way we manage our land, the way we've got methane emissions and nitrous oxide. So this is a very, very plausible emissions of effectively for energy only. I haven't got deforestation in here, but this is what our energy mix could look like in 2050, or between now and 2050. If we don't get to grips with our climate change, we'll still have heavy dependence on coal, oil, and gas, and probably only moderate dependence on renewable energy. If we start to take, climate change seriously, there's a lot we can do on energy savings, as I've already said, efficient transportation, buildings, and industry. We can grow our renewable energy sector, and therefore we would have less reliance on coal, gas, and oil. But what we need to do is couple coal, gas, and oil with, as I mentioned earlier, carbon capture and storage, because then if we do use coal, gas and oil, but don't allow the CO2 to get into the atmosphere, it's basically getting energy, but with no emissions into the atmosphere. So the sort of system we need to develop is a lot of effort on end-use efficiency, a lot of effort on renewable energy, and if we do use fossil fuels, we need to see if we can make this system of carbon capture and storage work in a cost-effective way and that is also environmentally sound. And this just expands it a little bit more. So, renewable energy. Two major things have happened that are really, really moving things in the right direction. One factor is the cost of solar photovoltaic energy. From 2000 to 2015, you can see from 0.75 all the way down to about 0.18. A very, very significant reduction in the cost of voltaic energy. But also, we've really got a huge advance in storage capacity. One of the big negatives about wind and solar is the wind doesn't always blow, and solar is very intermittent. And therefore, you always needed a base load, either nuclear or fossil fuel, for when the wind didn't shine, the wind didn't blow, or solar energy, the sun didn't shine. With storage capacity, it really has changed the game that you can use an intermittent energy source as long as you've got good storage capacity. This actually shows the investments in renewable energy. And as you can see, in the last sort of decade or so, gone up very significantly from a few tens of billions of dollars a year to of the order of about 200 or 300. In fact, it's gone back up significantly in the last 4 years. It's over $300 billion a year just in the investments in renewable energy alone in the last couple of years. Most of the added capacity has been solar in different parts of the world, although, as you can see, a pretty significant increase in wind energy and a very significant increase in solar, a little bit in biofuels, a little bit in geothermal, but not very much. So it's really wind and solar are the two new technologies. But also a lot of money, probably an equal amount of money, has been invested in end-use efficiency. I didn't bother showing that slide today. So overall, one's spending over $1 billion a year, over $100 billion, over $1 trillion a year, nearly $1 trillion a year on the energy system to make it more low carbon. This shows actually the different costs of solar energy in different parts of the world. 6.5 US cents per kilowatt hour, 18 in Indonesia, 2.9 in Chile, 4.8 in Peru. It varies, of course, on different countries, basically, of what their solar capability is. But it's now becoming really quite competitive to a new fossil fuel plant in many parts of the world. And in fact, in India, for example, their costs are way lower than the global average. Really, solar and wind are really starting to penetrate in India. And so what's the cost? You hear a lot about the cost of going to low carbon is exorbitant. And indeed, the estimate is to get to a 2-degree world, or round about a 2-degree world, you have to limit carbon dioxide to about 450 parts per million. We're already over 400 today, about 405, 410. And boy, we would lose about, by 2100, about 5% of GDP. It's irrelevant. It's peanuts. And the reason it is, we actually, our GDP is probably going to grow in a developed country. I would guess the US would hope to at least have a 2% growth per year. And a developing country, probably for the next 30, 40, 50 is at least 5% growth. China's been averaging 8, 9, and 10%. So the global growth rate is likely to be between 1.6 and 3% per year. So all we're reducing on an annual rate is a GDP, instead of being 1.6%, it would be 1.54%. Instead of 3%, it would be 2.94. In other words, yes, 4.8% of GDP sounds like a lot of money, but it's a very, very small delta on an annual growth rate. It really is. So the absolute number seems high, but in reality, it's slowing down the growth rate minusculely, absolutely minusculely, basically. And the other point that came out of the Stern report, the costs of mitigation are far less than the costs of adaptation. So what's needed? And I'll finish and I'll go through the last bit just very, very, very quickly. We need government, crucial, in partnership. That's the crucial bit, with the private sector and civil society. No one can do it alone. The private sector can't, governments can't, civil society. We all need to work together to change the way we've got climate change and my other favourite topic, loss of biodiversity. Therefore, we need coalitions working across sectors to really look, and we need to take a long-term perspective, cross-sectorial to policy formulation. And so the first thing is literally every government department has something to do with climate change or loss of biodiversity. So the first thing is for government departments, whether it's energy, water, agriculture, environment, finance sector, have to realize climate change is relevant to them. Every government department. The second thing, government's a stovepipe. The Department of Agriculture doesn't talk to EPA, doesn't talk to energy, doesn't talk to finance. We've got to get way apart from this stovepipe structure of governments, both nationally and internationally. The international structure is just as stovepiped as the national structure. So we have to work cross-sectorially. We've also got to recognize, as I've already said, climate change and biodiversity are not just environmental issues. They affect development. They affect food, water, energy, economic growth, human health, human well-being. So that has to be recognized. This is not talking about the environment. This is talking about development. The fourth is, what's our vision? What's the vision? Where do we want the US to be in 50 years' time? Where do we want the world to be in 50 years' time? And therefore, we have to start to develop a collective view of the vision for the future. The fifth challenge, fundamentally, is we've got to take a long-term view. We've got to get rid of the cycle of the next election or the quarterly profits of the private sector. We also got to make sure we all agree on what is the evidence base. What do we know and what don't we know? What uncertainties do we have? What are the implications of uncertainty? So I've chaired now 15 large-scale international assessments on climate change, biodiversity, agriculture, and on stratospheric ozone. And all of these are now the basis for international policy formulation, because we get, I mean, at the moment there's 1,200 scientists working with me on biodiversity. What do we know about the loss of biodiversity? IPCC has an equivalent number working on climate change. So we've got to agree on our evidence base, basically. The next is really making sure all relevant actors, all actors, and you've got them here, are part of the co-design and co-production of the evidence itself. We've all got to agree on what evidence is needed, and we've all got to agree on what it says. We also have to really look at the indirect drives that change: economic growth, demographic changes, trade, culture. We live in a globalized world. People that say the economic system is all broken, we have to start again, they're smoking something. We have a globalized world. Capitalism is the system we've got. The question is, how do we make it work for us, not the how do we fight against it. We need participatory processes. We need to get everyone engaged in decision making. This is not just for governments, it's not just for the private sector. Everyone needs to be involved in it. I've really said about the cross-sectorial. Technologies and policies are important, but individual behavior change, community, very, very important, basically. There's no such thing as everything's win-win. There are synergies in trade-offs. As we try to solve the climate problem, doing it one way can be good for biodiversity, doing it another way could be a disaster. And so we have to actually understand how the whole system works, that if we go, for example, on bioenergy to solve the climate issue, to move away from fossil fuel, it could adversely affect food production and adversely affect biodiversity. So we need to understand all of the synergies and trade-offs. So we need a holistic view of the world and how it's worked. And the last one is we've got to recognize, and most scientists don't, they're clueless. There really is incredible complexity in the socio-political system. And until you start to understand that issue, until you understand the political realities and the power asymmetries of who really has power, you actually can't change the system. You have to understand where are those vested interests, who has a vested interest in keeping an energy subsidy or a transportation subsidy or an agriculture subsidy. And so this is where the politics is unbelievably important. And so in conclusion, the world is very long on rhetoric. They all agree we've got a problem. Very, very short on action. We need to look simultaneously at economic, environmental, and social issues associated with climate change and, as I say, biodiversity. And this does require the right mix of policies, practices, technology, and behavior change. We must get the economics right. We must eliminate perverse subsidies, internalize environmental externalities, and for biodiversity, value everything we get from our natural world, both those that have market value and those that have non-market value. So thank you for your time. We have a major challenge in front of us.
Could you speak to the population growth on Earth? It would seem that population growth is a driver also.
Yeah. No, it's a very good point. It's actually a combination of two things. The reason I'm nervous, and I should have talked about it, the reason I don't like to take about population growth on its own is what really matters is consumption. The demand for food, the demand for water, the demand for energy. And that's based on two things, the total number of people we've got and the ability to purchase. So what we've got in the world today is we've got a growing population and we've got a growing economy. And the economy is growing fastest in developing countries. And so the ability to purchase in developing countries is going like this. The reason at the beginning I showed you 3 slides, where were the greenhouse gases coming from? And I showed China is now above America. So that's one issue. But per capita, we in the US still use far more energy per person and far more food per person and far more water per person than almost anyone in a developing country. So the challenge is, you're absolutely correct, limiting population growth is a key factor. Also, therefore, what we need is sustainable production of energy, food, water, and sustainable consumption. So the population issue is a major issue, but it has to be coupled in with the economic growth. So between now and 2050, we're already about 7.4, 7.5 billion people. It'll probably go to about 9.5 billion people by 2050, so another 2 billion people. But probably the world's gross domestic product will probably triple. So it's the ability to purchase as well as the total number of people. But a very good point.
Any other questions?
Could you talk a little bit about the Netherlands and their attempt to do carbon capture and their plans for...
Could you say that one again? I missed it, sorry.
The Netherlands have plans for massive carbon capture, and they're only at an initial stage, and they're... Can you talk a little bit about that?
Yeah, the interesting thing about carbon capture and storage is we've been talking about it for 20 years. I used to work in the World Bank and was chief scientist there for a while. And we were talking about it when I joined the World Bank, when I left the White House, and I joined the World Bank after I left the Clinton-Gore White House. And we were talking about carbon capture and storage then. And boy, the number of plants that are large scale in the world today is still almost non-existent. 1 or 2 in America, 1 or 2. What we need to do is actually really look to see, with pre-combustion or post-combustion, what's the energy penalty of using carbon capture and storage, because it is an energy penalty. What are the costs of carbon capture and storage? Can we put all the pieces together? We should be able to. And as I said earlier in the talk, can we keep the carbon in the ground once we've actually stored it? So I actually personally believe we need collective action of governments across the world working together with the private sector and probably doing something like 10 or 20 large-scale carbon capture and storage plants where governments collectively pay for it, private sector works with them. There is an issue then of intellectual property rights, of if you actually have a mixture of governments and the private sector, who owns the intellectual property. But we really need to do at least 10 or 20 large-scale plants, gigawatt plants, not these little, 50 megawatt plants, but really large-scale to see if it works. And some of us have been saying this for the last 10, 15, and 20 years. And what worries me is why the coal sector and the gas sector didn't invest in it, because it is the one way you then don't have to phase out the use of coal and gas. There was an incentive of industry to work with governments, but somehow it never came about.
So relating to the whole carbon capture technology, when you were talking about shifts in power and how we should be investing in power, I was a little surprised at how much carbon capture was there as opposed to investing more in renewables, which seemed like the more straightforward and currently technologically feasible approach. So I was wondering why you had that focus on carbon capture, and as long as we're shooting for the moon, why don't we talk about other kinds of geoengineering approaches?
Right, two very different questions there, which is good. These are models, they're these so-called energy models, integrated assessment models. Almost none of them, except for the one Greenpeace puts together, believes you can get enough penetration of solar and wind to really power the world. And their view is that you either need fossil fuels still at some level with carbon capture and storage, or you need some nuclear. No one believes nuclear is the solution, but I'm not an expert on nuclear, but I actually believe it is part of the solution. I did not get disillusioned with the problem in Japan. It was a very, very old power plant. It got hit by a 9.2 earthquake and survived it, and then it got hit by, a monstrous tsunami, basically. And the only reason it had a problem is they didn't have backup power. If they had backup power, the rods would never have overheated and it wouldn't be a meltdown. What I learned from that is the key thing is you don't build them on a place where you could get a potential tsunami, and you have backup power. And why they couldn't fly backup power, it wouldn't have taken that much. It really puzzles me. So I actually believe with new power plant, based on people that know it much better, orders of magnitude better than me, that nuclear can be part of it, but it's probably that 10, 20, 25%. I think if we could get renewables more, and the more we can do power storage, energy storage, the more that I think that has an opportunity. My view is, let's not guess what the energy mix is. Let's put a huge amount of effort in all renewable energy and carbon capture and storage. In other words, and end-use efficiency. So let's not guess what's likely to work. Let's keep our options open. Your other part at the end, geoengineering. Very, very intriguing. So I don't know if everyone knows what geoengineering is, but there's a couple of approaches. One of them is we put aerosols into the atmosphere, either in the troposphere, that's the lower part of the atmosphere, up to 10 kilometers in the pole, 15 kilometers in the tropics, or we put these aerosols into the stratosphere. And why do we do that? If you put aerosols into the atmosphere, it can reflect incoming solar radiation. The problem is we actually don't really fully understand how our Earth works. So are we being a little complacent believing that we can do this massive geoengineering and it will necessarily work? My view on it is I don't want to take our focus of more end-use efficiency, more renewable energy, and some people are just saying, let's not worry, let's just geoengineer. So my personal view is, let's do more and more research on it, some really sophisticated modeling of what would actually happen in the real world, and even do some large-scale experiments where all the governments of the world get together and agree on how you would do the experiment, open and transparent. So my view is, I don't want to ignore geoengineering, but I don't want to bet on it. So I think we should keep going on, make it go in a low-carbon economy. But if we don't get there, and all the evidence to me politically is we're not going to get there. We should continue doing research on geoengineering in case we need it. Now, some forms of geoengineering, even if it had a real problem, if you do it correctly and do an experiment correctly, if there is an adverse effect, the aerosols will come out of the atmosphere in 2 to 5 years. So in other words, you might have a bad effect for a short period of time, but it's a transient effect. So we've really got to think it through, but I don't rule it out, but it wouldn't be my first option, basically.
I'd like to go in two different directions. One is for long-term perspective. Why is it that I don't hear more about William Ruddiman's effort to try and identify when the climate first deviated from the Milankovitch cycles, which is about 8,000 to 10,000 years ago, and apparently due to the start of agriculture. And from that, how much have we depleted the Earth's ability to extract carbon from the air, which it had been doing, by burning all the forests in slash and burn type agriculture?
Yeah, I mean, it's clear that the Earth has these so-called Milankovitch cycles, and we've been in and out in the last, few million years, in and out of ice ages. There's no question at all about it. We're currently in an interglacial period, as you say. The next period is to go into another ice age. The only question is, will it be 1,000 years, 10,000 years, or another 50,000 years? We really actually don't know. But clearly, sooner or later, we might go into another. We go in the direction of another ice age. The interesting point is, if the Earth, because of human activities, warms up 2 or 3 degrees Celsius, it probably could stop us ever going into another ice age. Because even in an ice age, the average temperature difference is only 3, 4, 5 degrees Celsius. What we're doing, however, so yes, the Earth has been in balance for a long while between emissions of carbon dioxide and the emissions and the absorption. But what we're doing as humans is we're burning fossil fuels at such an incredible rate, the natural cycles of the oceans and the land can't keep up with our rates of emissions.
I fully agree with that. I just wonder why less long-term visibility of the long-term things that have been going on are not used, because it's a way of getting historians, anthropologists, and social media to look at all the developments that have been made in the last 10,000 years or so that have caused this, and that makes them more real. It makes them understand more things. Any case, the second is regards to nuclear. If you have breeder reactors, you have enough fissile and fertile fuels to power the Earth for something like 2,000 years with what we currently know to be economically viable recovery processes. If we do this, we can also design it, theoretically at least, to burn up all of the long-lived radioisotopes, so that only storing the waste for something like 100 to 300 years would get it to below the levels of ore in the ground now. Why is that not being addressed more clearly? Although I understand you said that you were in favor of looking more at nuclear.
Yeah, I mean, I'm not an expert on nuclear, but I listen to people like John Holdren, that used to be President Obama's scientific advisor. Listen to Dave King in England that used to advise Tony Blair as his chief scientific advisor, who actually looked fairly carefully at nuclear. And they're both actually quite optimistic. Nuclear can play an important role in the future evolution of energy. So my view is it should be looked at as one of the options going forward. Your point on looking back 10,000 years, I think is an interesting one. I mean, we should look sociologically at how development has occurred. The thing about it is, though, it's the rate of change. In fact, if you only go back to the beginning of this century, there was less than 1 billion people on the planet. We've now got over 7 billion. So the rate of change in literally the last 100 years is like this. So I'm not sure how much we would learn if we go back even 200 years, let alone 1,000 years, let alone 10,000. But it's something that sociologists might have an interesting look at.
Well, one certain area that would come up is the emphasis on religions of having as many children as possible.
Oh, sure.
And why that was necessary, and even when it was necessary, yielded such a slow growth rate because of technology not coming along. I mean, that's the sort of perspective, I think,
sure.
that can help sink the message home.
And it comes back to the first question on population. And I think, to me, one of the pivotal conferences ever was in Egypt, in Cairo in 1994, where they said to look at the demographic issues, you should look at 3 things: education of girls, as well as boys, empowerment of women, and culturally acceptable forms of contraception. As soon as you educate girls, as soon as you empower women, the birth rate goes down almost overnight, and they got it right. The trouble is, we never followed through on the policies across the world that it would take to implement very wise conclusions out of the Cairo conference. And you're right, we've made major advances in food, major advances in healthcare, etc.
Any other questions?
When you talk about carbon recovery and storage, are you talking about carbon or carbon dioxide?
Carbon dioxide. Yeah. You liquefy the gas before the gas escapes to the atmosphere. You trap it, you liquefy it, and then you subduct it. Now, it's been used by a couple of oil companies for what they call enhanced oil recovery. So the oil has come out of the gas well. So what they do is they pump this liquid carbon dioxide to force out the last vestiges. Statoil, in particular, in Norway, actually did it quite well.
Okay, thank you very much. Let's give Robert a big hand. Thank you very much for all the questions. And if you have any other questions, you can meet him afterwards. And before you go, we got a small gift to give you.
Thank you.